Hello, everyone. Thank you for joining me today as we will be discussing a very exciting topic complex reasoning with large language models. My name is Samuel Zhang, and this was done under the Delaware Space Grant College and Fellowship Program. In 2025, we're witnessing remarkable advances in AI capabilities, but one of the most challenging frontiers remains teaching machines to think through problems the way humans do, with logic, abstraction, and multi step reasoning. Today, I'll walk you through what complex reasoning means in the context of AI, why it matters, and the cutting edge techniques researchers are using to push these boundaries. Let me give you a roadmap of what we'll cover today. We'll start by defining what we mean by complex reasoning and how it differs from simpler AI tasks. Then we'll explore the motivation behind this research in its real world application. We'll divide the specific types of problems that challenge current AI systems, examine the current state of the art approaches, and finally look ahead to future directions in this rapidly evolving field. Let's begin with a fundamental question. What exactly do we mean by complex reasoning? To understand this, it's helpful to first clarify what we don't consider complex reasoning. So what is considered not complex? Tasks that are not complex typically rely primarily on pattern recognition, memorization, or surface level correlations. These are tasks where the AI can simply succeed by matching patterns it's seen in training data without requiring multi step inference. For example, completing common phrases, translating simple sentences, or answering straightforward factual questions. While these capabilities are impressive and useful, they represent a different category of AI performance than what we're discussing today. So, what do we mean by complex reasoning? Complex reasoning is the ability to use logic to solve problems involving multiple steps, abstraction, and generalization to handle new situations, not just repeating patterns. This involves several key components. First, the ability to break down complex problems into smaller, manageable pieces. Second, the ability to apply logical rules consistently across multiple steps. Third, the skill to abstract from specific examples to general principles, and finally, the capability to generalize these principles to entirely new situations that weren't directly seen in training. This is what separates true reasoning from sophisticated pattern matching. Now, let's examine how traditional large language models perform on these tasks. Like any technology, they have both strengths and weaknesses. On the strength side, LLMs excel at next word prediction, which is their fundamental training objective. They generate fluent and natural sounding language and demonstrate strong pattern matching abilities from their extensive pre training. They also exhibit what we call emergent behaviors, including what appears to be reasoning, although this is more like sophisticated mimicking of reasoning patterns they've seen. However, their weaknesses become apparent when we demand true multi step or logical reasoning. They lack built in structure for abstraction or planning. Their outputs can be inconsistent and perhaps most problematically, they often generate responses that sound plausible but are logically invalid. This is sometimes called the confident but wrong problem. So next I'd like to talk about the motivation and application of complex reasoning in large language models. So why does this matter? And why should we care about improving complex reasoning in AI systems? The applications are vast and impactful. In mathematics, we're looking at AI systems that can provide proof assistance, help with research, and even generate mathematical conjectures. In software engineering, we need AI that can handle multi step coding problems and debug complex systems effectively. In education, imagine AI tutors that could provide personalized instruction and detailed feedback based on genuine understanding of the subject matter. Understanding these limitations also help us diagnose where models fail and where human oversight remains essential. And perhaps most importantly, complex reasoning is considered essential for progress towards artificial general intelligence, the kind of adaptive, flexible problem solving that characterizes human intelligence. So next, let's look into the different problem types. First, symbolic reasoning involves manipulating symbols and expressions based on rules or structure. This includes algebra, formal logic, and program synthesis. The AI must follow precise rules without the ambiguity that natural language often allows. Second, computation. Computation requires executing multi-step numerical operations with precision. This includes arithmetic, approximation problems, and probability calculations. The challenge here is maintaining accuracy across multiple steps. Third, we have math word problems involving translating natural language into structured mathematical representation. So here we have an example. Bob has 4 apples and buys 2 more. How many apples does he have? This requires understanding the narrative and extracting the mathematical relationship. And finally, proof generation. Proof generation involves producing formal proofs to verify mathematical claims. This is perhaps the most challenging category, requiring not just correct answers, but logically sounding reasoning that can be verified. And with these different problem types, there's very popular data sets. And to study these problems systematically, researchers often use a data set focusing on different reasoning tasks. So we have symbolic mathematics focused on symbolic reasoning tasks. GSM 8K tests computational ability with grade school math problems. The math dataset challenges models with competition level math word problems, and Mini F2F provides formal proof generation challenges. These datasets allow researchers to measure progress systematically and compare different approaches. So now I'd like to talk about the current works. First, we have few-shot prompting. The first major approach. In few-shot prompting, we provide a language model with a small number of examples, input-output pairs followed by a new input. Mathematically, we can think of this as giving the model a prompt containing k examples and asking it to predict the output for a new input. Importantly, there are no updates to the model parameters. All learning happens through context. The model must recognize the pattern from the examples and apply it to the new case. We have an example on the next page. Here's a concrete example of few-shot prompting in action. We provide the model with a task description and 2 examples of simple arithmetic word problems with their answers. Then we present a new problem. Sarah has 6 balloons. She gets 4 more. How many balloons does she have? And the model will output 10 by recognizing the pattern of addition from the examples. This works well with straightforward problems where the pattern is clear and consistent. And I'd like to move to a real-world example using DeepSeek. So here we have an example of few-shot prompting. We have provided it with 2 examples as well as a new input and asking it to predict the output, and it correctly predicts the output. However, few-shot prompting has limitations with more complex problems, and this leads us to chain of thought prompting, which enables language models to perform explicit step-by-step reasoning by showing intermediate reasoning steps. The key insight is that we don't just show the model the problem and answer, we also show the reasoning process. Input examples include the problem statement, step-by-step reasoning, and the final answer. When given a new problem, the model learns to explicitly show intermediate steps before providing the final answer. And this technique has proven remarkably effective at improving performance on complex reasoning tasks. So let me show you an example of chain of thought in action with a more complex problem. So here we have a restaurant seating problem that requires multiple steps to solve. And we notice how the model's response break down the problem systematically, first calculating total capacity, then determining current occupancy, and then finally computing the remaining capacity. Each step builds logically on the previous one, and the model shows its work throughout. This transparency in reasoning not only leads to better answers, but also makes the AI's thinking process interpretable and verifiable. And I'd also like to show another example. So here we have an example of just a problem given. And then here it shows the different reasoning steps between and how it arrives at its final answer. So it reads, the problem is a pack of gum costs $2. Mike buys 3 packs. How much does he spend? So it first determines the objective and then restates the problem. and then it explains how we solve the problem. I should multiply the cost per pack by the number of packs. So that would be $2 per pack times 3 packs. Let me calculate that. 2 times 3 is equal to 6. Therefore, he spent $6. I should make I should make sure about the units. The cost is in dollars, and the answer should also be in dollars. The problem says a pack of gum costs $2, which means $2. And how much does he spend? So it is asking for a total in dollars. Multiplication is the right operation here because it is a total. It is a simple total cost calculation. If you think about it, adding $2 3 times would also work. 2 times 2 times 2, or 2 plus 2 plus 2 plus 2 is equal to 6. Same result. But multiplication is more efficient. There's no discount or tax mentioned, so I don't need to worry about additional costs. It's straightforward. So the answer should be 6. The problem is very simple, but I should present it clearly since it's a word problem. I'll state the word in a sentence or just a number with the dollar sign. Looking back, the question is how much does he spend? So I can say $6. He spent $6. In the context, since it is a response, I'll box the answer as per the instruction. The user says reason step by step, so I should show my steps, which I've done. Final answer, $6. And then here's an example with just their regular language model, not the large reasoning model, which we'll mention later down the line. Let's break down the problem step by step. Identify the cost of 1 pack of gum. Each pack costs $2. Determine the number of pack Mike buys. Mike buys 3 packs. Calculate the total cost. Multiply the cost of 1 pack by the number of packs. Total cost is equal to cost per pack times number of packs, equaling $6, which is correct as well. In building on chain of thought, researchers have developed even more sophisticated, structured reasoning methods. These enabled LLMs to explore multi-reasoning paths simultaneously through tree or graph structures. The key insight is that real-world problem solving often isn't linear, and sometimes our initial approach hit a dead end, and we need to backtrack and try a different path. These methods allow models to decompose problems into sub-problems, explore multiple reasoning paths, evaluate and select the best path, and iteratively refine solutions. So unlike linear reasoning, these methods allow the model to backtrack and explore alternative approaches when initial paths prove insufficient. This diagram illustrates how these structured approaches work. Instead of following a single chain of reasoning, as shown either here or here, the model can explore multiple branches, evaluate their promise, and pursue the most promising path. This mirrors often how humans approach complex problems. We don't always get it right on the first try, but we can recognize when we're on the wrong track and adjust our approach. So I'd like to now talk about the evaluation methods. How do we measure whether these techniques actually work? Evaluation in complex reasoning involves several approaches. The most straightforward is final answer accuracy, simply checking whether the model's final answer is correct. However, this binary measure doesn't often capture the quality of the reasoning process. The chain of thought evaluation goes deeper, verifying the logical validity and coherence of intermediate reasoning steps. This often helps us understand just whether it got there through sound reasoning. And then there's tool-assisted verification. Tool-assisted verification leverages formal checkers or code execution to validate proofs or solutions. This is particularly important for mathematical proofs where correctness can be verified algorithmically. Some people may have heard of mathematicians using Lean. Lean is a very commonly used formal proof checker. So now we're going to talk about the advanced techniques. So these go beyond the core approaches. Researchers often explore advanced techniques to further boost performance. First, we have scratchpad reasoning. Scratchpad reasoning gives models a dedicated space to work through problems similar to how humans would use scratch paper. So think about how you would solve a complex math problem. You don't just think it through in your head, you write down intermediate steps, trying different approaches, cross out wrong attempts, and gradually build towards the solution. Scratchpad reasoning formalizes this process for AI systems. The model is given explicit permission and structure to think out loud and work through messy iterative reasoning before providing its final answer. This has shown improvements in problems requiring extensive calculation or logical manipulation. Secondly, we have external tool usage. This represents a paradigm shift from expecting models to do everything internally. So just as humans would use a calculator for complex arithmetic or calculations, code interpreters for programming tasks, or search engines for factual information, AI systems can be equipped to access these same tools. When a model encounters a calculation that requires precision, it can invoke a calculator. When it needs to test code, it can execute it in a sandbox environment. When you need current information, it can query APIs. This hybrid approach combines the natural language understanding of large language models and the reliability and precision of specialized tools. So here we prompt a large language model to solve an integral by calling upon APIs. It will write code, which it then will execute and call on an API. This one using SymPy, symbolic Python. This one is using Wolfram Alpha. And then finally, we have fine-tuning approaches, which are creating what we call large reasoning models. And they are systems specifically optimized for complex reasoning tasks rather than general language modeling. So unlike traditional large language models trained on primarily next word prediction, these models are fine-tuned on reasoning-heavy data sets with explicit rewards for logical consistency and step-by-step accuracy. Some approaches use reinforcement learning from human feedback, especially focused on reasoning quality, while others employ constitutional AI techniques to embed logical principles directly into the model's behavior. The result is models don't just mimic reasoning patterns, but genuinely excel at logical inference. This is an example of a large reasoning model. It's DeepSeek's R1 model. And here you can see this model is specifically trained to be a large reasoning model, and it walks through step by step its solution to the problem. However, you may notice that this solution is actually quite convoluted, and the term often used is that it's overthinking. And for very simple problems, often just your base large language model will produce a very efficient outcome. However, with more medium tasks, we notice that there often large reasoning models are better at those, but when it comes to very complex problems, both models fail to solve a large majority of these kinds of problems. So there are limitations even with fine-tuned large language models, which are just called large reasoning models. So current future directions, looking ahead, there are several exciting directions that are emerging. One promising area is combining large language models with neurosymbolic AI, leveraging the strength of both neural networks and symbolic reasoning systems. Then we have self-reflective reasoning, which would allow models to revise their own reasoning steps, catching and correcting errors. So just like how a person would go back and check their own work, a large language model would go back and then question its own work. And then it could even say like, oh, this step doesn't make sense. And it would go back and revise that. There are multimodal approaches, which are just combining many different of the previously stated methods together. So it could use images, scratch pads, diagrams, or even neural symbolic AI as well. And then it's just combining it so that it has more than just one tool that it could externally call. And then finally, we need more robust benchmarks and data sets with step level metrics to better evaluate progress. So currently, many of the data sets just give out a final answer. It many data sets don't have like a chain of thought, don't involve chain of thought, and it largely currently just doesn't exist. So, in conclusion, I'd like to conclude the key takeaways from today's presentation. Complex reasoning represents a fundamental challenge that requires moving beyond pattern matching to multi step logical inference. The prompting techniques we discussed, particularly chain of thought and structured reasoning methods, have shown significant improvement in large language model performance on complex tasks. Our evaluation approaches must assess both final accuracy and the validity of intermediate reasoning steps. In the future of this field will likely integrate symbolic AI, self reflection, and multimodal approaches with more robust reasoning capabilities. The work we've discussed today represents just the beginning of a transformation in how AI systems approach complex problems as these techniques continue to evolve. We're moving closer to AI systems that can truly think through problems rather than just recognize problems.